Electromagnetic radiation has various forms. They range from radio waves to gamma rays. They all travel at the speed of light through a vacuum, which we'll see in a little bit is represented by the letter C, which is 2.998 times 10 to the 8th meters per second. They all exhibit a wave-like behavior, so we're going to be talking about waves, and it's a way for electrons or particles to transfer energy. Here we see the electromagnetic radiation spectrum. We have wavelength on the top, so this side is 10 to the negative 12th, and this is 10 to the 2nd. This side has shorter wavelengths. This side has longer wavelengths. We can see what shorter and longer wavelengths refer to in this picture down here. When you're talking about wavelength, it's the distance from crest to crest. So if you were standing on this axis and counting how many times a wave went past you, that would be the frequency. Waves that have shorter wavelengths would have a higher frequency. Longer wavelengths take a longer time to pass between you because there's a greater distance. So these shorter wavelengths are going to have a greater frequency. Longer wavelengths have a lower frequency. Make sure that you're annotating these on your notes at home. Since X-rays or gamma rays have a greater frequency, they're also going to have a greater energy. To help you remember that, you can think X-rays and radio waves. Of those two, radio waves, you don't put on protection like having to wear aluminum or lead. While if you go to the doctor's office, they're going to put lead on you to protect your bodily organs, or UV, you'd put on sunscreen. Because over on the left-hand side, these have greater energy. We can also see that on the top. Between UV, which is ultraviolet, and infrared, we have the visible spectrum. It ranges from 400 nanometers to 700 nanometers, and it ranges from violet to red. So that's what Roy G. Biv stands for. So red, orange, yellow, green, blue, indigo, and violet. So here would be our red all the way to violet. Spectroscopy, there's four main types of molecular motion, which occur when electromagnetic waves are used in spectroscopy to probe the structure of atoms and molecules, and or to determine their concentration. We have rotational, translational, vibrational, and electronic motions. So these spectroscopies allow us to see the makeup of different molecules. So rotational, to help you remember that, you can think a microwave rotates. So rotational for microwave. Infrared is weaker than microwave. Infrared is stronger than microwave, and so instead of just rotating the molecules, now they're going to start to vibrate. X-ray is going to be stronger, so it can remove core electrons. So for X-rays and UV vis, both of these are moving the actual electrons. X-rays are stronger than UV, so it can remove core electrons, while UV can only remove valence electrons because they're farther from the nucleus. And then gamma is stronger than all of these, so it's able to probe the deepest, and it can tell you the arrangement of protons and neutrons in the nucleus. So here's one type of question that has been asked on an AP question. Go ahead and pause the video and figure out which one you think this is. Restart when you have an answer. So just remembering that microwaves had to do with rotational movement. That was region Z. So region Z, the only one that says rotation is this last one. And that would be our answer. But we can further look at that question and see that infrared was stronger and caused it to vibrate. And then UV vis was talking about the electronic movement of valence electrons. So that would be electronic transition. The majority of this video is focusing on wavelength, frequency, and energy and the relationships between them. So wavelength and frequency are related in this formula. Wavelength is represented with lambda, and it's going to be in meters. So if wavelength isn't nanometers or centimeters or anything but meters, you're going to have to convert it because our c, or speed of light, is meters per second. This symbol is nu. It kind of looks like a V, but it's a Greek letter. It represents frequency, which has the units of either hertz, 1/seconds, or seconds -1. All of those mean the same thing. So it's recommended when you see the units hertz that you automatically just say that's 1/seconds. And as we saw at the beginning of this video, as wavelength increases, frequency decreases and energy decreases. So wavelength and frequency are inversely related. Frequency and energy are directly related. So this first problem says, what is the frequency if we know that the wavelength is 5.6 times 10 to the 5th nanometers? So we only know one equation for now, which is speed of light is equal to wavelength times frequency. We're looking for the frequency, which means we need to divide both sides by wavelength, giving us this as our equation. So we're going to put the speed of light on top according to our equation. We have 2.998 times 10 to the 8th meters per second. Make sure that when you're plugging that in that you're not hitting or writing /seconds. That slash is this bar here. So we have meters per second. Next, we're going to put our wavelength in. And according to our equation, wavelength should go on bottom. Doesn't matter where on bottom you put it, as long as it's on the bottom. And now I need to cancel my units. But I have meters and nanometers which don't cancel, so that means I need another step. I need to get rid of these nanometers, so the only way to get rid of them is to put them opposite. So nanometers is on top. I'm going to get rid of meters, so again, opposite of that would be on bottom. And from our unit conversions, we said that we're going to define them as putting the 1 with the larger unit. Meters is larger than nanometers, so we put our 1. And nano is 10 to the 9th. Make sure that you're physically canceling out your units to make sure that you're done. I can see that I'm left with seconds, and notice that seconds is on the bottom. 1/seconds, which is the same thing as seconds -1. So when you're solving for frequency, you want the time to be on the bottom. Multiplying and dividing that, we get 5.4 times 10 to the 11th 1/seconds. I could have also said hertz or seconds -1. Go ahead and pause the video and try this one on your own. Restart when you have your answer. So just like before, we're looking for frequency, so we're using the exact same equation. I have my speed of light on top. Anytime you're using that equation, speed of light's always going to be on top because you're either going to be solving for wavelength or frequency, which means you're going to divide by the one given. Wavelength is going on bottom, but unlike the last problem, notice that your meters cancel out automatically because they're both meters. So you don't have a unit conversion. In this case, you just divide, getting 3 times 10 to the 20th hertz. Remember that your units, you could have also said 1/seconds or seconds -1. So Max Planck determined that energy can only be gained or lost in whole number multiples. In other words, it's quantized. Once it gets enough energy, it can jump to the next energy level, and it can only go down in that same energy quanta. So we have two equations on top. Delta E is change in energy. Throughout the year, when we see that triangle, that means change. So the change in energy is represented by joules or J. And then H is Planck's constant, 6.626 times 10 to the -34th joules times seconds. So the equation on the left relates energy and frequency because H is a constant. But the one on the right relates energy and wavelength because H and C are both constants. The boxed in one is not on the AP formula chart, but the energy and frequency as well as our C equals wavelength times frequency are on the formula chart. And the boxed in formula is just a derivative of those two equations plugged in together. So you can either remember the equation, derive the equation, or just break up the problem into two separate equations. So what these equations represent is it's showing the relationship between the change in energy level and the electromagnetic radiation that would need to be absorbed or emitted to go up or down in energy. So if a molecule or an electron was going from the first energy level to the fifth energy level, it would need to absorb energy because it's getting farther from the nucleus. While if it went from the fifth energy level to the second energy level, it's going towards the nucleus, and so it's going to emit energy. So on this problem, they say that you have 450 nanometers, and they're saying what is the increment of energy that's emitted. So the first thing you've got to decide is which equation are you going to use. In this problem, we have wavelength, and we're looking for energy. The only equation that has both of those is this one on the right. Remember that we're using this one if it has to do with frequency and energy, the one on the right if it's wavelength and energy. So next we see, do I need to rearrange the equation? Well, it says what is the energy, and it's already solved for energy. So now I just need to start plugging things in. So I plug in my H. Remember that H is a constant. If you forget the number, look on your formula chart. Next, I'm going to plug in my constant, which is my speed of light, or C. Just like before, meters is on top, seconds is on bottom. And then wavelength needs to go on the bottom. So I can plug my wavelength in anywhere on the bottom. I have an empty space here, so I'm just going to plug it in down here. And I'm going to start canceling out my units. I see a seconds on top and a seconds on bottom. I see a meters and a nanometers. I can't just cancel out that M, which means I need to do a conversion. Nanometers is on bottom, so I need it on top. Meters is on top, so I need meters on bottom. Of those two, meters is bigger, and nanometers, there's 10 to the 9th. So I can continue canceling. Nanometers cancel out, meters cancel out, and I'm left with joules. Looking at the problem, it wants its answer in joules, not kilojoules. So that means I'm done. I just need to multiply and divide, giving me the answer of 4.4 times 10 to the negative 19th joules. So that's how much energy would be associated with 450 nanometers. This problem is similar to problems that they put on the AP test a lot of times where you're going to have to do a comparison. So reading the problem, it talks about the bond energy of an OH bond in H2O. And it says that that OH bond has 460 kilojoules per mole. Then they say, well, does a photon with a frequency of 3.08 have enough energy to cleave, which means break, this bond? So the first thing we need to do is look at the number that they're having us compare. We need to compare 460 to some value to see if it's going to be bigger or smaller than 460. So we need to put the number that they gave us in that same unit. We can't have a comparison unless they're in the same unit. Hertz and kilojoules per mole are not the same unit, so I cannot compare them currently. The next thing we need to do is say that Hertz is equal to 1 over seconds. All right, so are we going to use the equation on the left or the equation on the right? You said the equation on the left. You are correct. They gave us frequency, and we're talking about energy. So go ahead and pause the video and convert that frequency to kilojoules. Go ahead and go all the way to kilojoules. Restart when you have your answer. So we were looking for energy, so we don't need to rearrange. I have my H, it's going to go on top. And my frequency is also going to go on top. My frequency was 3.08 times 10 to the 10th. Notice the unit's 1 over seconds. So my 1 is on top and seconds is on bottom. I just don't write the 1. If you want, you could put in parentheses a 1 here if it makes you feel better. But we had said before we told you to pause to go ahead and convert to kilojoules. I have joules on top, so I need joules on bottom, and I'm converting to kilojoules. Kilo is bigger, so I put my 1 there, and kilo is 10 to the 3rd, so 1,000. Canceling my units, I see that my seconds cancel, my joules cancel, and I'm left with kilojoules. So that is 2.04 times 10 to the negative 26 kilojoules. But we want kilojoules per mole. Whenever we're solving problems using this equation or the E equals hc over wavelength, it's always per photon. So we need to get it from kilojoules per photon to kilojoules per mole. That's the main step people mess up on. Notice that these two numbers currently are nowhere near each other. Rarely are they going to have you compare two numbers and they be that far apart from each other. So that's also a hint that we're not done. So we're going to start with our answer, which was 2.04 times 10 to the negative 26 kilojoules per photon. The only thing I need to get rid of is photon and convert it to mole. So photon is on bottom, so I need photons on top, and I'm trying to get to moles. Well, I know that there's always 1 mole is equal to so many particles. Those particles are the same whether it be an atom, molecule, formula unit, or in this case, light. So 6.022 times 10 to the 23rd light particles, or photons, are going to equal 1 mole. So photons cancel, leaving us with kilojoules per mole. Solving that out, I get 0.0123 kilojoules per mole. So now these are in the same unit, and I can compare them. Although they're still pretty far off, they're nowhere near as far off as they were a second ago when we had to the negative 26th power. So does my 0.0123 kilojoules have enough energy to break a 460 kilojoule bond? So make sure that you finally answer the question. No, the photon only has that much energy, which is not enough to overcome the 460 kilojoules per mole in the bond. This problem is similar to the last problem. The only difference is it breaks it up for you a little bit better. So go ahead and pause the video and find what the energy of a single photon with a wavelength of 340 centimeters is. Restart when you have your answer. So the first thing you should have decided was which equation you needed to use. You should have said the one on the right and used it. Make sure you always have your equation written and rearranged if needed. In this case, we were looking for energy, so no need to rearrange. H should have went on top, as should your speed of light. Make sure you're putting that S on the bottom so you can cancel those units. Wavelength should have been on bottom. Again, I can put it here, I can put it over here, as long as centimeters is on bottom. Centimeters doesn't cancel with meters though, so I need one extra step. And I know that meters is bigger than centimeters. So I get 5.8 times 10 to the negative 26 joules. Remember that that was how much energy is in one photon. So now we need to find out how much energy is in a mole of photons. So now we're going to do that last step that we did in the previous problem. Go ahead and pause the video and restart when you have the energy in a mole of photons. So in this problem, we should have started with our previous answer. Remember though that we need to put photon on the bottom because we need to get rid of that photon. And putting that unit there helps us determine where the photon and where the mole goes. Since photon's on bottom, photon has to go on top. Also, I'm looking at how much energy per mole, so I know moles is going to go on bottom. 1 mole is equal to the speed of light, or not the speed of light, the Avogadro's number. So we get 0.035 joules per mole. Some simpler questions that you could be asked is just which of these involves an electron needing to absorb energy and which ones release energy. So looking at that first one, we're going from the third energy level to the first energy level. So it's going towards the nucleus, which means it's going to want to go towards the nucleus because that nucleus is positive. Therefore, it's going to release energy. For B, it's going from the first energy level to the third, so it's going outwards. It's going away from that nucleus. It's going to take energy to pull a negative electron further from that positive nucleus, so it has to absorb energy. Go ahead and pause the video and do C and D on your own. Restart when you have your answers. So C, you should have said absorb. It's getting further from the nucleus. And D, you should have said release. It's going towards the nucleus. We have two types of spectrums, continuous spectrum and line spectrum. A continuous spectrum is what you see with a rainbow or when light goes through a prism and it separates into all the different colors. In a line spectrum, it indicates the energies that are allowed for a particular element. Remember that because energy is quantized, the energy goes from one step to the next. It's not continuous. And the energy that's quantized is different for each element. So how it works is in this vessel, we have a gas of an element. It's heated through high voltage and light is shown through a prism. On the detector plate, only certain wavelengths come out. So for this element, which is hydrogen, we have 4 wavelengths: 410, 434, 486, and 656. We can see hydrogen, helium, oxygen, neon, iron all here. Each of these bands, again, is particular to for a certain element, so it helps us identify which elements are in a given sample. This is how we can identify. So here's a type of problem that you could see. It says we have an unknown mixture and we have 4 different gases. Identify the 2 gases in the unknown mixture first. Restart when you have an answer. So you should have said gas A. Gas A is the only one that has a line here at the very beginning. And then gas D as well. So notice those 2 are for gas D, and then this one is gas A. So A and D. Think about how this emission spectrum is produced in terms of energy states of an electron. If you need to refer back to the picture we had on a couple of slides ago, this one, and then come up with a short answer response for part B. Restart when you have your answer. So here we can see that energy is being applied to the sample, which excites the electrons to a higher energy state. So they go to this higher energy state, but they can't stay at that higher energy state, so they start to come back down. When they come back down, they release energy at these set wavelengths.